Let's do the last two problems. So these are projectile motion problems. Number 10, we have the projectile launched horizontally. So it's going to follow this path, kind of a half of a parabola. And we're looking for the height of the table. So we're looking for h here, which is the height of the table. Now this is almost the same thing as delta y, because delta y is the vertical displacement, and the ball goes from here to here. So this is delta y. So if we solve for delta y, we'll get a negative number, and if we just make this number positive, it'll be the same exact number as the height. So we're looking for delta y, so let's look at the y direction and write down our givens. Well, when we're launched horizontally, that means that we're not launched vertically, so v initial y is 0. And then the acceleration in the y direction is always negative 9.8. And we're given the time it takes 0.3 seconds to get to the ground. So we are given three variables in the y direction. We don't even have to look at the x direction. We can use an equation to solve for delta y. So I chose to use this equation right here. Delta y is VOYT plus 1/2 AYT squared. Cross out the first term since VOY was 0, and I plugged in the givens right here, and it gave me about 0.44 meters. Number 11 is the second case of projectile motion where the projectile is launched at an angle. So we're looking for the maximum height of the stone. So we're looking for this height. Now the problem was not very clear, so let me just change the problem and say, what's the maximum height of the stone above the top of the building? Since that's what I actually solved for. But if it asks for the maximum height above the ground, then you would have to add the height of the building to it as well. So if we're just looking for above the top of the building, then we're just looking for from here to here, and that's going to be our delta y. So again, let's look at what we are given in the y direction. Well, if we're looking for the maximum height, that means it must stop in the y direction. So v final y is 0. And then we're also going to have the acceleration in the y direction is negative 9.8 as always. And then we need one more. We're given that the initial speed is 15 degrees at an angle of 53. So what it's giving us here is that this vector here has a magnitude of 15 meters per second. That's vi. And then the angle here, that little angle right there, is the 53 degrees. So the y component of the initial velocity is going to be opposite that angle. It's going up here, so it's going to be 15 sine of 53 degrees. So once again, we are given three variables in the y direction. So we don't need to look at the x direction just quite yet. So if we're looking for delta y, I used this equation here, vfy squared equals v initial y squared plus 2ay delta y, and crossed out this term, solve for delta y, move voy squared over to the left side here, and then divide everything by 2ay, and I got 7.32 as my meters as my final answer. And part B, what's the velocity of the stone as it hits the ground? So it's hitting the ground right here. It's going at an angle. So that velocity has an x and a y component. So we need to find each of them. So for this problem, we don't really care about what happens over here. We can redraw this again, and we are going up there and then getting down here to the ground, but I'm just going to consider the path from here, from the initial point down here to the ending point. So I don't really care about what happens at the peak. If I look at the path from the beginning to the ending point, then the displacement of the ball is from here to here. And I'm given that displacement. That displacement is negative 35 meters, since it's the height of the building but negative. So by considering these points of the problem, this is the beginning point, this is the ending point, then I'm going to have enough variables. In the y direction, I also have my v initial y, same as before, 15 sine of 53 degrees. And I also have my ay, same as before, negative 9.8. So again, I have three variables in the y direction. This will allow me to find v final y. So I'm going to use the same equation that we used up here, but this time when I solve for v final y, I'm going to take the square root of each side. And so I'm going to get the square root of v initial y squared plus 2ay delta y. The square root of all of that. And that's going to give me negative 28.8. It's negative since it's going down. And then I need the x component of that final velocity. So the x component of the final velocity is the same as the initial component, because the velocity in the x direction never changes. So it's going to be 15 cosine of 53 degrees, which is about 9.03. So now that we have the final x and the final y, we can use the Pythagorean theorem to put them together, and you'll get 30.2. And then again use the inverse tangent of the y component over the x component, and you'll get 72.6 degrees. Since VFX is going this way and VFY is going down, and you know that VF is going this way, this angle that you found here is below the horizontal. So that's why I called it 72.6 degrees below the horizontal.